Greetings, students. Today we are going to have a little introduction to exponents. Now I know that you've worked a little bit in class, done some factor string work, and done some exponent work with squares. So this is an introduction to exponents, but it's also a review from some things that we've talked about in the last week. So let's go down to the basics and make sure that we're looking at things the same way. If I were to write this, what does that mean? Right, that means 5 plus 5, which is equal to what? Correct, 10. So now I want you to watch this. Here we have a 5 with a little raised 2. In this situation, this 5 is considered to be the base. And what we call this is the exponent. And we're going to be talking about what does that exponent mean. Okay, so we're going to be talking about what does this exponent mean, but first we need to know how to say this. One way we can say it is we'd read it as 5 raised to the power of 2. But this can be said differently, and it's quite frequent when we run across it in exponents, and we call it 5 squared. But what we want to know now is, what does it mean? So we remember 5 times 2 equals 5 plus 5. 5 to the second power equals 5 times 5. So you see the difference? This one is 5 plus 5, and this one is 5 times 5. And that 5 times 5 is 25. Okay, so here's the next thing. On the left we have 2 times 4, and on the right we have 2 raised to the 4th power. So we think, what does 2 times 4 actually mean? It will be 2 plus 2 plus 2 plus 2, which is 8. Now 2 raised to the 4th power, what does that mean? Means 2 times 2 times 2 times 2. So what does 2 times 2 times 2 times 2 equal? 16. Okay, so now over here I'm going to write 3 times 2, and over here I'm going to write 3 raised to the second power, or 3 squared. So 3 times 2, what does it mean? 3 plus 3, which is 6. So what does 3 squared mean? 3 times 3, which is 9. So I'm going to throw one at you, don't get too mixed up here. But what if I said x raised to the 5th power? What would that mean? Yes, x times x times x times x. And now that I'm looking at it, I probably shouldn't have used x's because they look like times symbols, but actually this dot in between the x's are the times symbols. It's just another symbol for times, and you really should get familiar with it because you will be seeing that in the future. And look at that. I need one more x. So x to the fifth is x times x times x times x times x, and that's what it represents. We don't have a solution for that because we don't know what x stands for in this case yet. So now let's look at 3 to the fourth power. What does it mean? It means 3 times 3 times 3 times 3. So how do we calculate that? So some people look at it and they say 3 times 3 is 9, 9 times 3 is 27, and they go 27 times 3, and then they kind of get stuck. So I would like to remind you that when we have multiplication in order, we can group them and multiply them in any order with the commutative property. So I'm going to group them. 3 times 3 is 9, and this 3 times 3 is 9. So then if we look at those two, 9 times 9 is 81. Much easier to do than to look at it as 3 times 3 times 3 times 3. All right, so I wrote this up there, and so how would we say this? Well, we would say this is 2 raised to the third power. But this also has a shortcut name, and we would say that that is 2 cubed. And so the shortcut for the exponent raised to the third power is cubed. Just like raised to the second power is squared, we call this cubed. So I just wrote this up on the board here for you. How would you write that as a word statement, or how would you say that as a word statement? That would be stated as 6 to the seventh power. And that would mean 6 times 6 times 6 times 6 times 6 times 6 times 6, which will be a pretty big number, and a calculator would be a good tool to have for something like this. Okay, and just to kind of work that, instead of trying to do that all by grouping and doing that in our head or even on paper, remember last week we took out our calculators and we found a couple of the different signs. One of the signs was a caret, and one of the signs was an x to the second power. Well, there is also a sign that is either a y to the x power or an x, I think it's a y to the x power on those calculators that have the x to the second power, and or the caret. So this could be push the button base 6 and then press the caret and tell it to raise it to the 7th power, and then that will equal the answer. And I don't have a calculator here, so I'm not going to do that. Or you can say 6 and then hit the y to the x power and tell it that it is raised to the 7th, and that should also calculate that for you. And so finally, after all of that work just with naming and writing out those exponents, I want to go back to a number that you did with your factor strings, and that was 24. I believe that you worked that and said it could have been 12 times 2, it could have been 6 times 4, could have been 8 times 3. You could have looked and said, oh, well, that 8 actually is made up of 4 times 2, and then times that 3. So we have this is another way to write the 8 times 3. And so that gives us a longer factor string. And we can take that one step further and we can look at that 4 and say, well, that 4 actually is a 2 times 2. And then we have this 2 and this 3 that we still have to keep multiplying through. So if we look at that, we have a very long string that just kind of grew by breaking down all the numbers that could continue to be broken down. And if you notice that the numbers that are left are all prime numbers. So it seems that it does not go to the next slide, so when it stops, whoever's running this can try to get it to the next slide, and it's okay if you can't get it there. It just has a factor tree on it, and all's good if you don't see that. You got most of what I was aiming to do with exponents. Thanks. And while I'm at it, I have decided that I would take and give you a quick factor tree example here, taking that same 24 and looking at, let's look at it again with our 8 times 3. Okay, so I took my factor of 8 and my factor of 3. If I multiply them together, I get back to my original whole number. And then I can look and say, well, that 8, I know, can be 4 times 2. Notice that it was 4 times 2, not plus. And 3, can't do anything with that because that's a prime, so I said I'm done with that one. But I can look back here and I still can work with my 4, because my 4 still can be broken down into its factors, which are 2 and 2. And so now I look at that, and 2 I can't do anything with, and 2 I can't do anything more with because their factors are taken. You don't want to go down to a 1 because that changes nothing. So right now I have the 2 times 2 times 2 times 3. I just take my factors at the end of each stem of that tree and I put them back into a string, and that will come back to 24. And interestingly enough, you can see that this way, when I break it up, is 6 times 4, because it all means the same thing. And I just wrote that factor string out again. The 2 times 2 times 2 times 3 is 24, because I just want to make it clear that that's the longest factor string that I can come up with, because they are all broken down to their prime factors. And we call that prime factorization. Prime factorization, which should be familiar because you saw that in the little pretest at the end of Unit 1 test. So I do hope that you learned some new things or just got stronger at some things you already have learned. And I hope that makes your day bright and sunshiny, because it sure does mine.